Hi everyone, I'm Malcolm. I'm a second year student at U Michigan. My major right now is pure math, but I want to double major in honors math and computer science. This is my EECS203 IA application video, and today I want to talk about the cardinality of the set. So in lecture, we didn't prove that our set of real numbers is uncountable. So today I want to prove it. But how do I prove it? I think it's pretty hard to just I think it's pretty hard to prove it just by definition, because we need to prove that there doesn't exist any bijections which map from the set of real numbers to the natural numbers. So I decided to prove it in another way. So first I want to show that the open set 0 to 1 is uncountable by using the Cantor's diagonal argument. And then I want to show that the set of real numbers and the open side 0 to 1 have the same cardinality by using the Schroeder-Bernstein theorem. So once I prove these two claims, I get the conclusion that R is uncountable. Okay, so let's begin. Okay, first, I want to show that 0 to 1 is uncountable. And I make a claim that every countable subset of 0 to 1 is a proper subset of 0 to 1. So here's my proof. Suppose A is an arbitrary countable subset of 0 to 1. Since A is a countable subset, there exists a bijection which maps from A to the set of natural numbers. So we can rewrite A as the set of A naught, A1 to the AN and to many other countably many elements. So since every element in A is a real number, so we need to rewrite them in the decimal expansion. So suppose we have A naught, A1, A2, and A1 equals to 0 0.1, so we can rewrite it as 0 0.1000 and so on and so forth. And A1 equals to 1 over 7, which can be rewritten in as 0 0.142857, 142857, and so on and so forth. And A2 equals to pi over 4, which can be rewritten as 0 0.7857, 53, 98, 16, 33. So since we use the decimal expansion, we need a new notation to represent the digits in the decimal part. So I define the capital D sub j AI to be the jth digit in the decimal part of AI. And here's some examples. So for example, D1 A naught is the first digit in its decimal part, so it's 1, and D3 A1 is the third digit in its decimal part of A1, so it's 2, and D5 A2 is the fifth digit in the decimal part of the A2, so it's 9. Okay, so once we have decimal expansion and new notation, we are going to prove the A is a proper subset of 0 to 1. So to prove it, we just need to find the element x, which is in the set 0 to 1, but x doesn't belong to A, the set A. So since x is element in the set 0 to 1, so its integer part should be 0, and its decimal part, I define it in this way. The I plus 1th digit in the decimal part of x is equal to either the I plus 1th digit in the decimal part of AI plus 1 or 0. So for example, here's A naught. So the first digit in the decimal part of x should be the first digit in the decimal part of A naught plus 1. So it's 1 plus 1 is 2. And the second digit in the decimal part of x should be the second digit in the decimal part of A1 plus 1. So it's 4 plus 1 is 5. And its third digit in decimal part of x should be the third digit in the decimal part of A2 plus 1. So it's 5 plus 1 is 6. and we keep doing that for every element in A. So since we create the diagonal, so it's called a Cantor's diagonal argument, and in this way we create an X which has at least one digit difference with every element in the A. So it's obviously like to show that X doesn't belong to A. So but X is in the set 0 to 1, so the set A must be a proper subset of 0 to 1. So we finished proving our claim, and once we get this claim, it's pretty easy to prove that 0 to 1 is not countable. So suppose for a contradiction that 0 to 1 is countable, and we know that 0 to 1 is a countable subset of 0 to 1. So by our claim, we know that 0 to 1 is a proper subset of itself. But we know that it's a contradiction, so we prove that 0 to 1 is uncountable. Okay. Okay, after I prove that the open set 0 to 1 is uncountable, I also need to prove that R and 0 to 1 have the same cardinality. So here I want to use the Schroeder-Brisbane theorem, which talks about for any sets A and B, such that A's cardinality is less than or equal to B's cardinality, and B's cardinality is less than or equal to that of A. So we have a conclusion that A and B have the same cardinality. So in other words, we just need to find the two injective functions, f which maps from A to B and g which maps from B to A, because the property of the injective functions give the same argument. So to prove that R and 0 to 1 have the same cardinality, we just need to find two injective functions, f which maps from R to 0 to 1 and g which maps from open set 0 to 1 to R. So for f, it's pretty hard to find it directly. So I find two sub-functions, f1 and f2, and let f to be f2 compose f1. So here's a way I define function f1. f1 maps from R to -1 to 1, and f1x equal to x over 1 plus absolute value of x. And f2 is a function which maps from -1 to -1 to the set to an open set 0 to 1, and f2x is equal to 1 minus 1 over x plus 2. And for g is pretty easy because we just need to use the identity function, which is obviously injective. So before we prove the f equals to f2 compose f1, we need to show that f1 and f2 are well defined and f2 compose f1 is well defined. So for f1, since x is a real number, if x is positive, so f1 plus f1x is equal to x over 1 plus x, which is equal to 1 minus 1 over 1 plus x. Since x is positive, so the denominator is always positive. So and 1 over 1 plus x is greater than 0 and less than 1. So we have f1x is in open set 0 to 1. So if x is equal to 0, so f1x is equal to 0 over 1 plus 0 is 0. And if x is negative, we have f1x equals to x over 1 minus x and equals to minus 1 plus 1 over 1 minus x. Since x is negative, so 1 minus x is always positive. So 1 over 1 minus x is greater than 0 and less than 1. So f1x is in the open set -1 to 0. So in any cases, f1x is in the set -1 to 1. So f1 is well defined. Okay. So for f2, since x is in the open set -1 to 1, so x plus 2 is greater than 1 and smaller than 3. So 1 over x plus 2 is in the set 0 to 1. Then we have f2x equals to 1 minus 1 over x plus 2 is in the set 0 to 1. So f2 is also well defined. Since f1's image or codomain is a subset of f2's domain, then we know that f2 compose f1 is well defined. So we have f is well defined. And then we want to show that f is and then we want to show that f1 and f2 is injective. So f is also injective. Okay, then I want to show that function f2 is also injective. So by definition, for any a and b belongs to the open set -1 to 1, such that f2a equals to f2b, I have 1 minus 1 over a plus 2 equals to 1 minus 1 over b plus 2. So we have 1 over a plus 2 equals to 1 over b plus 2. So we have a plus 2 equals to b plus 2, and we have a equals to b. So f2 is also injective. Since f is equal to f2 compose f1 and f1, f2 are injective, then f is injective. So we have the cardinality of R is less than or equal to the cardinality of 0 to 1. And since G is an identity function which maps from 0 to 1 to R, and is obviously injective, so we have the cardinality of the open set 0 to 1 is less than or equal to the cardinality of R. So by Schroeder-Bernstein's theorem, we have the cardinality of R and equals to the cardinality of 0 to 1. Since 0 to 1 is uncountable, which we proved earlier, then we can show, or we can get a conclusion that R is uncountable. So which completes my proof. Thank you.